Hello. As in the last lecture video, we are discussing regarding the modeling of the mechanical system. That is the previous is the basic modeling of the mechanical system, how it can be done with the help of mass, spring, and damper system. Now, here we are taking some example of different combinations of the and interconnection of the different masses, different springs, different dampers, and so on. So this is one example of a system. This can be any type of system in industrial version that can be modeled with like this. Now once any industrial devices, mechanical devices can be modeled like this, so from there we can get the transfer function corresponding to that, or mathematical modeling of this type of systems may be done with the help of some differential equations only. So let me check how can it be done. Step by step we have to discuss it. See, first of all we have to study this diagram. What is here? There is a mass m1 and a force is applied at the end of this mass m1, and once a force is applied f, then definitely there is a displacement of this mass with respect to equilibrium positions, that is x1, and corresponding to that velocity generated is b1, right? And this mass is connected with some damper b1, and this mass m2 also. This m2 is connected to spring and damper on both sides, where due to this force, whenever this force F is applied, definitely this mass will be moved by its equilibrium position, from its equilibrium position, by amount of x2. And once this mass m2 is displaced, definitely there will be some velocity associated with it, which is termed as b2, right? And this mass is directly connected with this rigid surface through this damper b2. Now how to get the differential equations? Yeah, you will get, or we will get, two differential equations because of two masses connections, two masses connected with the system. So if the masses are 2 or 3, so that's what that the order of the system will be like that. So you see, for single mass m1, we have to draw the free body diagram corresponding to this. And when you will draw the free body diagram corresponding to any mass, right, say either m1 or m2, we have to just consider first that where, in which end of the which mass the force is applied, right? First of all, we have to consider this mass m1, because the force, external force, which is applied here, F, which is applied at the end of this mass m1. So first, coming to the free body diagram of mass m1. What is the free body diagram? See, number one, you see FBD for mass 1. How to write it? Simple. This is your mass m1, and this force is acting here, right? This is the external force, and once this force is acting, so displacement of this mass m1 is x1 and velocity b1. So definitely some inertial force, that is m1 d2 x1 dt2, will be acting the opposite direction, right? Next, what comes, this body is connected to b2, and see this b2, another end is connected to this rigid surface. Try to understand what I'm telling. This b2, one end of the b2 is connected to the mass m1, and another is connected to the rigid body. So actually, when this mass m1 is displaced, what happens? The force exerted in opposite direction by this damper will be proportional to the velocity b1, right? So what is the force in opposite direction you will get? You will get the force in this direction, that will be b2 d x1 dt, right? So this is the force due to thus b2, right? So now another part is that this b1, right? b1 is also connected to m1. So once this m1 mass is moved due to the force F, definitely some restoring, that means the opposition force will be applied by this b1. So b1 force is also the force which will be opposed due to this damping coefficient or viscous damper in the opposite direction. So there will be another force What will be that force? That is actually, this. Now consider this damper. See, and so what happens here, you see this b1 is connected to the m2 mass as well as m1 mass, and once this force is acting in this direction, definitely x1 is the displacement of this mass, corresponding to the displacement of this mass m2 is x2. So what is the resultant force? Resultant force will be equal to b1 d dt of resultant displacement. Resultant displacement means this end x1, actually movement of the mass we are considering, so this is x1 and here this is x2. So resultant displacement in this direction we will consider as x1 minus x2. So x1 minus x2 is the force exerted in opposite direction uh, once the force F is acting on m1. So this is the actually free body diagram for mass m1, right? And similarly we will write the free body diagram for m2 body. So FBD for body m2, mass m2. So when we will write this free body diagram for m2, what you have to write? Just you will take, this is your m2 mass, right? And once this force, this free body diagram for the m1 is over, now see there is no direct force acting on this m2, but as this force when exerted to it, we have in the last lecture described that these are the basically the storage elements. So energy is stored here when you will just remove this force. So what happens? This M2 is connected to this B1 in this terminal and a spin constant, spin with spin through this rigid body. So due to displacement of x2, what happens? Due to displacement of the x2 itself, its displacement is x2. So definitely what happens? You see there will be m2 and displacement is in these directions. That means if opposition force, inertial force m2 d2 x2 dt2, this will be actually working in the upward directions, right? And you see this is displaced by x2, so spring force will be opposite to that. So here will be, you will be getting spring force. What is that? K1 into x2. Because why K1 into x2? See, K1 is the spring which one is connected to my rigid body, that is no displacement, and x2 is the displacement in this direction. So x2 minus 0, basically K1 into x2 is the force which will be opposing the motion of the m2 in this direction, right? So these spring forces will be acting upward direction. So this is the direction of the spring force. So what is there in this direction then? Basically you see there's nothing, but actually this end of the m2 is connected to b1, and when this b1, that means when we were developing the free body diagram for m1, what happens? You see this is a force exerted in this direction, and uh, a storage elements damping coefficient factor was there b1, for which this b1 ddt of x1 minus x2 was the force in these directions. So this is the storage element, so that much of force will be acting as the force when m2 is acting alone. Understood? I am repeating. So this is the b1 body which is connected to the m2 in this direction. So you see if this m2 is connected and m2 is displaced by x2, definitely inertial force mt into dt x2 dt2 is there, and as the spring is connected here and bodies try to move downward direction, definitely a force, opposition force k1 into x2 will be coming into play. And so in this direction, what is the force? That force is the same force which has been developed by the B1 when the force F was acting on M1. So what is this? This is basically B1 ddt of x1 minus x2, right? So you see these are the two free body diagram. Once these two free body diagram for the entire mathematical model of this system is done, that means you have to write the differential equation corresponding to this system and corresponding to this system. We will write now the differential equations. These two differential equation we will write will be the actually governing equation for this overall system, right? So now D'Alembert's principle, that is very easy. What is the outward force in this direction for m1? You see, this is total force. I can write it m1 d2 x1 d22 plus b2 dx1 dt. This is outward direction, this is outward direction, plus b1 ddt of x1 minus x2, right? That is equal to the outward direction force in this downward direction F. So this is the mathematical equation or differential equation 1, and from this favor diagram what you will get, you see outward direction force, that is m2 d2 x2 dt2 plus k1 x2, right? So these two in the outward direction, the above the m2 equilibrium positions. Now below the equilibrium position, what is the force? That is equal to v1 d dt of x1 minus x2. So equation number 2. These are the two equations. Basically, once you have to get the mathematical model of the system, that means you have to derive the differential equation corresponding to the whole system. So corresponding to the whole system is, this system is divided into two parts according to the free body diagram concept. To analyze any mechanical system and corresponding to mechanics I have described. So these are the two equations we will give the mathematical model for this corresponding system, right? And once you can write these two equations, now you can get the Laplace transform on both sides, and by using Laplace transform you can get the corresponding f versus x1, or corresponding if you can put the value of x1 here, then also you can get the value of f versus x2, right? From here you can solve the value of x1 in terms of f and x2. That is not actually required for our analysis. So up to this you can get the mathematical modeling for the system I have described. Next I am going to discuss about another system which is also comprises of the you see mass, spring and damper in different combinations, right? So this is our number 2, system number 2, and you see structure of the line, and this is one spring, this is the rigid body, and this is your damper, say b1, and you can see it b2 and k2. This spring and dampers are connected with, say, mass m2, and say this is a cart system, 2 mass cart system, and here you see this is your a1 and this is your b1. Another mass is connected, say m1, say force is applied here, right? So this is a 2 mass cart system where you are just this is one rigid end, and these are the elements you can now recognize. This is spring with spring constant k2, this is damper, this is another damper, this is spring constant k1, m1 and m2. A force f is applied here, or you can say this force similar to that. Actually this here even we are just taking this mass by using some force f, right? So basically when this type of system is given to you, you have to identify what is the displacement of this. Say if you applied force f here, or similar force here also, you can apply the same structure, gives you the same response kind. So this is x1 and corresponding to velocity v1, this mass is moved x2 corresponding to velocity v2, right? So what happens, you see, first of all, again, like the previous mathematical modeling of the system, you have to draw the free body diagram corresponding to mass m1 and m2, and see, these are f1 is equal to 0, f2 is equal to 0. This is the friction coefficient with the surface. These are basically, we can take it or talk it, tell it as the some wheels, like. So we have to ignore this because the value of this friction coefficients are 0. So we have to consider rest of the forces acting on different bodies like m1 and m2. What is this? See, first of all, we are considering the free body diagram FBD for mass m1, right? So what is the force? I can say this free body diagram I can use like, so this is your m1. So m1 is the mass and this force is outward, so you can take it like force F, or you can give this forces in this direction also. So we have considered this outward force F, and corresponding to that, what is the displacement? That is x1. So inertial force, that is m1 d2 x1 dt2, this will be acting on the outward direction, no problem. Now see this b1 this is the damping coefficient, viscous damping coefficient, b1. For that, the force which will be coming into picture, that will oppose the motion of this m1, definitely, right? So this will try to oppose the motion, so definitely there will be another, okay, right, like this force which will be opposing the motion of this mass m. And now this b1 is connected to both m1 mass and m2 mass, so definitely the resultant displacement in these directions, what will be the resultant directions? This is x1 for mass m1 in this direction x1, and this is the when you will apply this force here, definitely this mass of the cart will also be trying to move in this direction, so that will be displacement x2. And this b1 and k1 both are connected to both the masses, so actually resultant displacement is x1 minus x2, as we are considering the mass of the m1, right? So resultant displacement, if this x1 minus x2, so this will be the force, this is b1 x1 minus x2 dot, or ddt of x1 minus x2, we can call it. Similarly, what is the force? Opposition force due to the spring is also connected to this m1 and m2 both. So resultant displacement when you apply this force F is x1 minus x2. So due to the spring, what is the force? That is k1 x1 minus x2, right? This is the free body diagram for mass m1. And see, next step, we will consider the free body diagram for mass m2, right? What is the free body diagram? How it look like? Say this is our mass m2. So m2 is the mass and displacement is x2. So and force is in this direction, so this is the opposition force, that is m2 d2 x2 d2 2. This is the force in these directions. And what is the force? Opposition force. Here opposition force will be applied uh, due to this spring k2 and damper b2, because when this m2, this mass m2 is moving in this direction, what happens? This b2 and this x2, sorry, k2 will try to oppose the motions, right? So what is the opposition forces exerted by k2? One end of the k2 is connected to this rigid body, and one end is x2, so resultant displacement is x2 minus 0, that means x2. So due to k2, you get k2 into x2. Similar to that, b2, due to b2, what is the force? This is b2 x2 dot, right, or dx2 dt. And in this direction, when you just consider the mass m2, then what will be the actually forces? External forces is not there, so the forces acting on the mass m2 to move it by a displacement of x2, that is done with the help of storage elements k1 and b1. Because once a force was applied to m1, some energy stored, which is due to the force k1 and which is due to the force b1. So these are the two forces, k1 x1 minus x2 and b1 x1 dot minus x2 dot. They are the resulting forces. So once these forces will be acting, corresponding to that, this is the opposition force. Now once you get the you see these two free body diagrams for this complete system, what you get the differential equation corresponding to that, right? And corresponding to that differential equation, you can write the differential equations itself. So I will write the differential equations corresponding to the two free body diagrams, and we give you the mathematical model for that two mass guard system in practical situations, right? So I will write, or you can write it similar, very easy. That is m1 d2 x1 dt2 plus b1 ddt of x1 minus x2 plus k1 x1 minus x2. This is f. This is equation number 1 from the free body diagram 1. And from free body diagram 2, you see the total force in the outward direction. What is this? This is outward direction total force, k1 x1 minus x2 plus b1 x1 dot minus x2 dot. So we will write like k1 x1 minus x2 plus b1 ddt of x1 minus x2, right? So that will be equal to the total force, total outward force. That will be the principle of our D'Alembert. So this is equal to k2 x2 plus b2 ddt of x2 plus m2 square dt square. That's it. So this is way how we can just get the mathematical modeling corresponding to any system. Actually, first of all, any system which is actually operated in industry, the mechanical system, first of all we have to get the block diagram in terms of mass, spring and damper. Then by using the free body diagram and mechanics, Newton law of motions and D'Alembert's principle, we can get the free body diagram corresponding to the system. And once you get the free body diagram of the system, definitely it will be very much easier to find out the differential equation corresponding to that. And by using the Laplace transform, you get the corresponding system functions as required. And you see, if these two equations will be combined into a single term, then that will be a fourth order system, because this is a second order differential equation. You can identify it because say this is a second order differential equation. So second order differential equation means d2x1 dt square. This is a second order differential equation. Similarly here also this is a second order differential equations, right? So when these two second order differential equations will be merged into one, and you will get a fourth order differential equation. So the total system can be a fourth order system, right? And you see this is how the mathematical modeling of the mechanical system can be done. In the next class, this series lecture series for control system, we will learn some analogous system, right? We will learn about the analogous system. Analogous system, in the last video also I have discussed what is analogous system. That means in case of electrical system or in case of mechanical system, two systems will be given to you, or one system will be given to you. From that, equivalent to that, another system can be developed. That is known as the analogous system. Okay, in the next video we will discuss about it. Follow it.